You calculate the images.
Yes.
And the co-kernel is z squared plus z form. One of the generators of the free portion is transcendental, don't worry about that. The other generator of the free portion is one of the sections of the elliptical function. The second section is obtained by taking the first section and adding on twice the generator of the torsion type. So that's why, because that section is torsion, right? So if you do twice it, you add the torsion bit on twice and it kills it, and then you get something that modulo the image is equivalent to the original section. So you sort of see all of that, but the sections are definitely not
Getting it straight. We are reintroducing Andrew for the second part of his talk. Hooray.
Thank you. Okay, so today I want to give a definition of versions of categories. And then after that, I want to move on to a couple examples. That's the plan. Certain I'll get back to that.
Yeah.
Okay, so recall last time. So we defined. So perverse Chauffeurs. So perverse chauffeur was basically an analog of so this fairly classical sort of construction of the data that's analogous to a perverse sheaf on a disk. So this is analogous to classical expression of data equivalent to a perverse sheaf on the disk with some stratification. Okay. So what we did was we basically took this expression of what a perverse sheaf on a disk with stratification sigma is. So this is a bunch of vector spaces and a bunch of maps. And then we translated this into the language of DT categories, where these vector spaces were DT categories and the maps were not just functors, but spherical functors. But if you remember, we also had like a sort of a characterization given by Kapranov and Sheckman of perverse sheaves on any surface in terms of data associated to a skeleton of that surface. So what I want to do today is to sort of, increase the amount of information in sort of our description here. I want to give you sort of what's probably the most of a definition of a perverse sheaf of categories on a Riemann surface with a specific set of points representing the singularities. Okay, so what I need to do is the following. So we decided last time, or I sort of explained that if we have a skeleton K and a one-valent vertex, the linear so the linear algebraic data that we should associate to a perverse sheaf on such as around here with the singularity here should be a pair of vector spaces and a pair of maps going back and forth between the vector spaces. I called these phi and psi last time, and a pair of maps satisfying this condition, and then that the identity plus RF is invertible. Okay, so that's, I guess, the first. I mean that's that. So we characterize this, but then we also realize that the right analog of this in category theoretic language is that we have two functors going back and forth with f spherical. in the sense of analog and echo. So that was, so the first characterization here, the one with vector spaces, that was important when we defined perverse sheaves on a disk with stratification given by a certain set of points. But when we went to trying to define perverse sheaves on a Riemann surface with stratification given by a set of points, we also needed some sort of description of the data associated to a point where the skeleton looks like this. So we gave Kranov and Shekman's sort of characterization of perverse sheaves, or more precisely, the restriction to the skeleton. Here's such a point last time. Here, a point like this. Say k-valent or n-valent vertex. In a skeleton K. What we need to do is we need to give a category theoretical analog of this characterization of Kranov and Shekman. So KS stands for Kranov and Shekman. So we need to give a category theoretical version of this of their definition, or I guess their characterization. And so, from what I understand, so the most general sort of appropriate analog of this is what's called an n-spherical functor, n+1 spherical functor. I don't know what the n's are, but nothing, I guess, has been put out about n-spherical functors yet. So what I'm going to do is I'm going to sort of cheat a little, and I'm going to give you an analog of the example of this that I gave you last time. So I gave you an example of how the sorts of data that Kranov and Shekman tell you must go here. And this was something like, you take a vector space and you take n-1 copies of this vector space and you define specific functions, sort of homomorphisms to B. And so what I want to do is I want to give you a category theoretical version of this. And then I'll use that to give you a definition of a perverse sheaf of categories, which is coordinatized with respect to some skeleton K. Okay, so here's the first definition. And, okay, so let C be a DG category. So C the DG category. And let F is going to be an ordered collection, one F, let's say N, where Fi, these are all functors from some DG category AI. And we'll let A denote the ordered collection of categories A1 and where AI are DG categories. Okay, so these are functors and these are DG categories. So this is my let's go with Roman sequence. Okay, so then what I want to do is I want to define sort of a category built up out of all this data, a new category built from all this data. So then the category, which is product F A, I don't really know good notation for this, but this is what I use, is the category whose objects are, so these are pairs, alpha and mu. So the way to think about this, alpha is just an n-tuple of objects in A1 to An, but I'll write this as a diagonal matrix. Alpha is a diagonal matrix with objects A1, A2, zeros everywhere except the diagonal, and An. So this is mostly just a sort of heuristic way of writing this, but not this one. Zeros. Okay, so this is a matrix like this with AI. These are the objects of the AI. So I'm taking in n12 objects. Each of them lives in one of these categories. And mu is again a matrix. So it's going to live in the sort of diagonal here. So mu1, 2, mu2, 3, mu1, 3. So everything lives above the diagonal. 0, let's say mu, n, and etc. So it's all zeros here until we get to n. So it's a bunch of mui's where mu, let's see. So mu ij is in f I j, and I need the degree here, and so I think this is j minus I. It's 0. I'm going to get the degrees wrong. I'll just put this here as something to put there, but I think it's somewhat wrong. Satisfying the condition that b mu as a matrix plus mu squared is equal to 0. This is a more apparent condition. Yeah, I need some sort of different degree here. But on these sort of on here, these things are degree 0, I think. Anyway, there's some degree. Okay, that's right. Okay, so it satisfies a more Cartan condition. Okay, so these are my objects, and these are the homomorphisms. Are just going to be upper triangular matrices, homomorphisms. And hom, say alpha, mu, beta. So let's let so the elements of AI. So let's say that alpha is the matrix with AIs on the diagonal, and beta is the matrix with PIs on the diagonal. Let's say prod F A L, so degree here, is our upper triangular matrices. With entries G and J in here I think I do know the right degrees. L minus J plus I in image category C between F, I, A, I, J. Okay, if I is not equal to J and GII, and C, L, if AI, right? So the diagonal elements are distance between the same objects sitting inside of the category A. Whereas, if we want to take comps between objects I and J, since they're not actually living in the same category to begin with, in order to compare them, we need to map them into the category C using the functor f, the functors fi, and that's what we do here. Okay, I mean, composition is going to be matrix multiplication, and we're going to get, I mean, you can define a differential that sort of just does essentially the thing that you need it to do if you want to define a differential on such things. So I'll give you, I mean, let's just write down.
Is that really Hom C for GII?
Let's see.
Little AIs.
Tom. Oh no. Sorry. Yeah. Sorry, it's AI. Yeah, it's Tom and AI. Okay, so just to, I mean, to tell you why is this an interesting thing, I'll give you two different facts about this. So, that, which is essentially due to, well, I mean, this is a generalization of a definition given by Kuznetsov and Muntz. And so, I mean, I'll attribute this back to Kuznetsov and Muntz, but it goes back even further than that, really. Soul construction, I think, I mean, to some extent, goes back to Tabuda, maybe?
Tabuda?
Sorry?
What was the?
Tabuda, I may be pronouncing this wrong. So is that if I take the homotopy category of what I've defined pi and A, this is going to have a semi-orthogonal decomposition into categories H0 to A1, 0. Right. So it's a semi-orthogonal decomposition, and another fact, again, I think, on a proof of this, this is essentially Kuznetsov and Muntz. If AI, when writing this again, if so let's say H0 of some GG category B as semi-orthogonal decomposition given by subcategories A1 to AN. I should be using different letters. Let me use different letters for this. Let's say D1, DN. So if this is true, then let AI be subcategories, be the full subcategories of A, such that, well, made up of objects A, such that the class of A, so this means I'm going to take the class of A in the homotopy category. So the homotopy category has the same objects as the category, so this is just the corresponding object in H not of A. So if this is actually in BI, this is going to be an object of AI. So AI is sort of the lift of BI to the category A. To the category B. So if this has a semi-orthogonal decomposition on the triangulated level, we lift each of these categories to a subcategory of the DG category E. Then each of these full subcategories emits an embedding. So we're just defining these full subcategories to be subcategories to be made up of objects so we can embed them. But so at I, you this embedding BI into B, the obvious embeddings. And let's see, so the category, so again, just let this be this collection A1 AN, these lifts, and let F be the functors F1, Fn, these functors here, then if we take the corresponding category, pi Fa is quasi-isomorphic or quasi-equivalent, sorry. So the point is that if you have a semi-orthogonal decomposition, you can reconstruct the original, this category by taking sort of lifts of each of these things, gluing them together, and this just gives you the original. So, so this is just like a nice way of sort of formalizing semi-orthogonal decompositions and sort of constructing semi-orthogonal decompositions from just different functors. Say about this. Okay, great. So that's my construction. And so the reason I want to talk about this is that, well, it is so that I can define, a category that goes sort of into these end-value vertices of my skeleton. So I have a skeleton here, right? And I want to define a category which should sort of play the role of the fiber of a constructible sheet of categories on the skeleton at this point. Okay, and so what is the category that I should put here? So, so this definition taken sort of for granted will define, so the category, so if C is a DG category, it will define, so what I'll call a n minus 1 C. This is going to be the product. This is, let's say, I'm going to take sort of the n-fold product of each of the entries of twisted complexes over C, and the set of functors is the identity. So maybe let's just give this better notation. So what I'm going to do is I'm going to let all of these categories just be twisted complexes over C, and all of these functors just be the identity functor. Okay, where all AIs are twisted complexes over C, and all FIs are the identity functor. Okay, so how should I think about this? Well, my objects in this category are going to be collections of objects, A1, A2, A3, dot to AN. And I'm going to have objects here, so maps here, mu1, 2. So this is degree 0 enclosed by the Moore-Cartan condition. This is mu2, 3, again degree 0 enclosed, n minus 1n. Degree 0 closed by the Moore-Cartan condition. And then there's going to be these extra homomorphisms that were sort of the above diagonal parts of this matrix, big mu. This is n minus 1. It shows. These are just complexes, or not complexes, just bunches of objects and arrows like this, 3, etc. And mu1, 3. This should basically, so the things that were read above that diagonal in this matrix mu, these were just these homomorphisms, which must be degree 0 enclosed. But so if you think about what this matrix says, if you look at the things that were above the diagonal, then what's going to happen is that these are going to have to give you basically explicit homotopies between the composition between these two morphisms and 0. And so the above the diagonal, these are going to give you sort of, different sort of homotopic relations between these morphisms, the lower morphisms. Okay? So you should think about these things as actually like representations of the quiver AN minus 1 in the category C. So in some rough sense. AN quiver, AN minus 1 quiver. Twisted complexes over C. Okay, so that's how you should think about this category AN minus 1. So what are some nice properties of this category? Well, there's a bunch of nice functors from this category. So there's functors. And so, I mean, what I want to do is I want to say that this is the right category to be the stop of some sort of constructible sheaf here. So I mean, I want the categories along the edges to be the category C. So what I need is I need to provide a functor from this category AN minus 1 to the category C for each of these edges emanating from the n-valent vertex. So there are certainly functors Fi going from AN minus 1 C, twisted complexes over C, which just project the function A1 AN minus 1 onto AI. So you project onto the ith object in this. Then there's, so for, this works for I not equal to n, or say I equal 1 to n minus 1. And then there's a functor Fn, which sends AN minus 1C, and this is the reason for using twisted complexes here, which sends, well, the object alpha mu, basically, I mean, roughly the same object in twisted complexes over C, but this really goes to, so I have to take this, so objects in twisted complexes are sort of formal direct sums of objects in C. And so, I mean, roughly what you're going to do is send these things to, let's see, Fi applied to AI, where I goes from 1 to n. And then we're going to shift this by negative I. And then we're going to apply, so we also need a matrix of homomorphisms, which is sort of formally of degree -1, which satisfies more Cartan condition, and that is just this. So you get n functors into the twisted complexes over C. Actually, should just be objects in C. So this goes to twisted complexes over C by just mapping onto AI, which is in C, and then C sort of naturally embeds into twisted complexes over C. So that's how that functor works. Let's see. Oh, okay. So great. So this is the sort of category that I want to put at a vertex like this. So it may seem a little bit asymmetrical that the way I define this. I have a numbering from 1 to n, but there's a cyclic symmetry on this category that sort of rotates all rotates these functors. So for instance, just to ANC admits cyclic symmetries which rotate, which sort of rotate or shift in the sense Fi by 1, not n. So for instance, if we take the category, so A of this is going to be made up of objects which are just basically pairs. Let's say A1. Let's write this as matrices. Okay, so that's what the objects look like. So we just have a diagonal matrix with two entries, and then we need some sort of matrix of homomorphisms, which in this case is just going to be some mu here. So mu is in A1, A2, 3, 0, closed. Okay. So those are the objects of A3C, and which are homomorphisms in C. And so how do I see the cyclic symmetry here? So the cyclics, so what I have is essentially the following. In this case, the way you should think about it is that I have a vertex with 3 edges coming out. So I put my category A to C here. Then I have a functor going here, which sends this object, say this object here to A. This object A1, this object here to A2, and this object here goes to essentially what's the mapping cone of mu. So F1 is alpha mu A1, F2 sends alpha mu A2, and F3 sends alpha mu to the cone. And so, of course, you see that there's a symmetry here. Because, we're just looking at this mapping cone, it's roughly this. 2 mu cone here. And we have some homomorphism here, tau. So the functor is sending A 1, 0, 0, 2, 0, 0. If this sends this to, let's say, 2, mu, 0, 0, tau, 0. So this functor is a this is a quasi-equivalence going from A to C to A to C. And you see that if you sort of apply this 3 times, you get back to where you started, but with a shift by 1. Okay. So my point is just that, despite the fact that the way I define these functors seems sort of like it depends on some sort of ordering here that I took, all it really depends on is the cyclic ordering that I have, because these functors will just sort of exchange representations. Okay. Okay, so now I'll give a definition of a Perverse sheaf of categories. This is sort of partial definition, but essentially this should be enough to, in any case you really want, this will work. So Perverse sheaf of categories. On a surface S with singularities in sigma, data. So 1, skeleton K in S. Okay. So I mean, a skeleton in S is i.e. a subgraph, graph embedded. Embedded in S, such that S deformation retracts onto K, such that so the vertices K contains sigma. So every point in sigma must be a vertex of K. So the simplifying assumption that I'm making is this star, which is that if B is in sigma, then B is univalent. So that's a simplifying assumption that I make. So that I can basically shove things like these AN categories at all n Bailey vertices. I guess maybe to be careful, I'll put a second star here, is that B is not in sigma. B is not univalent. Okay. These are two conditions that could probably be removed, but I'm just being kind of lazy. Okay. So the second piece of information is a category, or the second set of pieces of information is a category CV for each vertex B in vertices of K, and a category, and this is going to be a funny way of saying it, but it's probably the right way of saying it, something like that. A category CE for each edge K, such that all CEs are equivalent. Okay, so I mean, essentially what I'm saying is that I'm only choosing one category for all the edges. I mean, all the categories of the edges are the same. Category for each vertex, category for each edge. So, and then the third thing that I want is that the following conditions. So I have functors big F and E for each adjacency between B vertices of K and B edges of K. I need functors for adjacencies, and the functors must satisfy the following conditions. So the following conditions. So, okay, let's say if B is n Bailey, that is, it's one of the vertices which is not contained in the set sigma, and for n greater than 1. So that means it's true. So then, there is some cyclic ordering of the edges adjacent to be such that f v going to ei is equal to phi ei multiplied, composed with some I. So the FIs were what I defined before. So they were projection onto, oh, wait. Okay, so I forgot a condition. I'm really sorry, I forgot a condition here. So the condition is that, goodness, sorry, CV is equal to AN minus 1C if B is N named. Okay, sorry, I was trying to give you, say something about these functors by, assuming that they were actually equal to these categories, the CV was equal to this category CV without telling you that that category had to be CV. Okay. Okay, so the CV composed with some phi EI, where phi I is an equivalence of the category C. Okay. Okay, so this is my first condition. And then B, if B is univalent, that is that B is in sigma, then the E, so it's only adjacent to one edge because it's one valent, so this is spherical. Okay, so that's my mostly general definition of perverse sheaf of categories, which is K coordinate. So this refers to the skeleton K. We need to choose a skeleton K in order to define this perverse sheaf of categories. But after that, basically all you need to do is you need to sort of choose spherical functors for each of the for each of the one-valent vertices in sigma, and you need to choose these autoequivalences for each of the adjacencies. Okay. So now let's give some examples. Okay, so I'll spend some time just describing a couple examples, and then after, I guess, a little break, we'll talk about what the categories of global sections for these examples are and how this might relate to mirror symmetry. So that's the most general definition. So, basic example is that if we have a K-coordinatized for Schober, and just to recall what this data is, so this is the data of a bunch of points inside of the disk. So we have sigma, and then we have some sort of skeleton that we choose, so that these are like legs going off to some point P. So this is Q1, Q2, Q3, Q4, and then we have some point P, and we choose another edge going off to the boundary of the disk. Okay, so if we have this perverse Schober, so this is this skeleton, so that's K, this is K, and then we have the data of Fi going from AI to the category C for each, or bless you, for each sigma. So that's the data for a Schober. So then we get a canonically defined K-coordinate coordinatized C just by sort of, I mean, this is most of the data that's needed for a perverse sheaf of categories, the K-coordinatized perverse sheaf of categories. We just haven't specified the category associated with vertex P, and we haven't specified the functors associated from the adjacencies between P and the edges going to QI. So just by grouping it, with the data, so I'll call it CP. This is just whatever the number of things inside of the set sigma are. So a set of the size of sigma plus 1. This is the category C that goes here, and Fi of big, so F P and Pi is just equal to the function of Fi. For some cyclic orientation, it doesn't really matter. Well, I mean, it's not just some cyclic ordering, right? I mean, because since this is a graph embedded inside the surface and it sort of deformation retracts onto the graph, there's a canonical cyclic orientation that you obtain once you have an orientation on the surface. Right? This is essentially like a small generalization of a grouping graph. That's what K is. So you have a canonical cyclic orientation. So this cyclic ordering of edges adjacent to a vertex is given, and it should be given by sort of the same one that comes from the orientation of the surface. Okay, so here, I mean, we have like you have a bunch of functors and a bunch of sort of categories, and they just, I mean, what this K-coordinatized perverse Schober is just like a some sort of diagram of categories essentially. Right? So one way to think about this is just like a diagram of categories, which is sort of dictated to you in sort of its structure, or at least part of its structure, by the surface S and the skeleton K. Okay. And so in this very simple case, there's really not much to choose. I mean, you just choose functors for these points, and that's essentially. Okay, that's one example.
So part of your definition is singularities.
Mm-hmm.
I'm just saying that
Yes.
it's a K-coordinatized perverse sheaf of categories on a surface S with singularities.
In sigma, in a set sigma.
Right, I'm just saying that whole phrase. So the word singularity in this context doesn't mean anything we thought it meant before.
No, I mean, so I think this is the language people use when they talk about perverse sheaves. They say it has singularities in certain finite set. So this is where where it's not a local system.
Right.
And so if you think about this as something coming from maybe like the push forward of something on a sheaf of something going down, then the singularities are sort of actually critical.
So the phrase with singularities modifies perverse sheaf. Just when I parse it, the phrase a surface S with singularities appears. You don't need anything classical about it.
And a surface, comma, with singularities.
Right, but the singularities refer to the perverse sheaf.
Yes.
Good. Okay. Thanks.
And so the second example that I'll write down is something like this. So this is something that's sort of canonically associated to a category with an autoequivalence. So roughly canonically, plus some skeletal data. So let's see the DT category. And let phi be an autoequivalence of C. we'll let K be the following. So it's going to be, well, let's let S be S1 across closed unit interval. And let's let K be this. Just draw a picture. I don't think I need that. So it's this skeleton inside of S1 across the closed unit. Okay, and so we have two vertices. We have, say, E1, E2, and we have, say, E1, E2, E3, So if I want to specify a first sheaf of categories on this, well, I'll let sigma be empty. Okay, so I have no singularities. But this doesn't mean I have to do nothing interesting, because I do have these points that are vertices in my skeleton. So I do need to do something interesting here. So C V1 is equal to C V2, and this will be A3 of C. And then C of all the edges, by decree, these are all the same. I'll let them be just the category C, or maybe twisted complexes over C, just to be more consistent. And okay, I've got categories for each of my edges and each of my vertices, and now I need functors. So I was calling these. So let's say FB1 goes to, what's it adjacent to? E2. So this is going to be just the functor F1. So this is the one going from A3 to the orientations, right? So let's choose some orientations of these things. Okay, sure. So then F1 going to E3. This will be F2. And F1 going to E1. Let's let this be F. So this is just sending one of the two objects to the first one. This is the sending the pair of objects AB to the second one, and this is sending it to its couple. Okay, so that's my first sort of set of functors. Then I need to give you functors for each of these guys here. So I'll write those down. So FV1, V2, sorry, going to let's say V2. This is just F1. And I need V2 going to V3. So this is where the only interesting thing going on here happens. Is I'll send that to the composition of phi with F2. Yes, okay, that's fine. Then 4. And that gives me a first sheaf of categories on this cylinder with, and so with sort of, you should think about this as sort of the monodromy going around the central cycle. This is just given by phi. So this is, you should think of this as a local system of categories. On the cylinder with monodromy given by phi. Okay, so that's essentially what the state is representing. I mean, I mean, I like to have these edges going off towards the boundary, and maybe you'll see a little bit about that later. That's maybe at this point just decoration. Okay, so I guess I'll break now. You guys want?
If you want, I mean, we can have a 5-minute break and just.
Yeah. Okay.
Mm-hmm.
Then we'll go for another
Like
Hour.
an hour.
hour, that's right.
We're halfway.
We're halfway. We're talking about. I mean, I won't circulate it, but it's very hard for me to follow the details from just chatting at the board. And then, you know, I can see if there's something more direct in there. So I think, depending on how you proved it, some of the results related to the existence of the special logic and vibration fiber types might be applicable, might be useful.
I have a question. So, is it easy to see that you said this ion, you have like 3 ion, ion? This is the unique one?
Oversee, that's easy.
Yeah, overseas, yeah. Oh, how do I see it?
好像是就从那个
Easiest way to see it is to
ANC
use
打
the
到
wire
C，
stress.
就把它打到 DI 给。
So put your ion on infinity
对，但是那是另一个
and
是
it
small
drops the
advice
degree.
small 大概
对对，它不是第三个
So I
requirement，
have this
它有一
one.
个对一个 adjacent vertices associated quantum，
对，
然后 such that这个
Yeah.
是
So generically, this is going to have, this is a rational, this
嗯
is going to have.
你说那个小的，
对对对
对对对，就是那个，
What
啊，
do
就是
we
大
do?
打分，
就是它 FI 是小 FI 是从 A
0.6 or something.
ANC
Something
打
like
到 C，
0.6.
Yeah, okay. So you have your
No,
response,
the-
but
the-
because of,
哦 ANC 的东西，
the I9, just put I9.
Yeah.
Or 0, whichever you prefer. But
就从
because of
ANC
that,
有
so if
有
your
N
ion
个
is infinity,
map
it's
打到
gonna
C，
effectively
就是从
draw
F1 到 F，
嗯
就是小 F1 到小 F。
，OK，
There's a Kodaira table,
因为
对
ANC 就是说
vanishing
一个
order,
category，然后
so it tells the
vortex
order
数
of
是那个 category，
vanishing.
对对，就是哎对，就那些 ANC，
2,
就是
3, go.
就是那个 vertex 的
Corresponding to
stuff。
fiber types.
但我是说它这个 ANC 就是
What's
这个
Q2?
stock
G, G2. So for you, it's
开那个
Okay.
任何，
So the order of vanishings,
Uh-huh.
these
它就是
guys
这个 stock 是
affect,
Yeah.
Is
correspond
it, do you, is it like take out?
然后
Yeah, it's a consequence.
然后
Okay.
Right. So from that, you can reduce constraints of the AMP. Constraints on the AMP you can
I see.
最好是 C 给
I
力
mean, this
之后，
particular
本
case
身
is
就
forcing
是
you to
A，
find an example, so there's an
所
old
以唯一可以
classification.
选的就是那些 auto equivalence 跟那个
All the forcing
但是
plus.
它是想到一个 n 跟一个无法分数是那个 an 规范，是这个意思，就
So
是它
that's
第
easy
二个
application, that's actually easy to work.
But
Again, even for first principles, this is not hard, right? There's only forcing
Why-
fibers, so
Uh-huh.
you know you
No.
can send 3 of them, 0, 1.
Yeah.
哦 n
So the
为
only question is
就
the
是
fourth.
a a
Well, the fourth is going to be completely determined by the discriminant condition in this case.
它懂 a n 减 e c 这个
Yeah, because really, this like vanishing order, I only know that.
对，
Yeah, I think the vanishing order condition can
You only know,
start
like,
with-
Yeah.
So it could be that the vanishing order
就是有
is
分
not
个 category 不还是
relevant. If
如果它是
if
完
this
全
has
对
I know that this has like some, like up to some, like
就我就没看到
maybe I
这个
would
的地
differ
方
by something
Oh.
with this, right? Because like you have AT replace AT by this, then and BT by another function like this, then you still have the same vanishing
这
order.
个
But it seems that even I do this reprioritization, you get the same thing.
就是当这些都是一样
This。is completely rigid.
Yeah. So
this
I believe this is true.
Yeah.
And so, but I'm just saying that, like, if I just do this, like, I can have this reprioritization out.
Yeah, that's
But
a freedom, that's a freedom, but.
Yeah, but actually, the end is,
那我觉得这个
they should pinch it down to be the same thing, but it's not exactly.
Yeah, but I mean, in this case, I'm setting this up because if you have like a type 4-star fiber,
Yeah, yeah,
2-star
yeah.
fiber, then these degrees drop. This won't drop because this is IN type. This is a vanishing order, this is discriminant. But that's fine. So I mean, you know that this would vanish in into order. So the point is, if you compute the discriminant,
Yeah.
G2 minus G3 squared or whatever it is. And the fact that, put this in infinity,
Make it edge, yeah, category.
and then the fact that this vanishes towards 9 at infinity means you drop its degree. So that means G2 minus G3 squared, whatever that is, isn't degree 12, it's degree 3. So I mean, this is all it is, right? So instead of being degree 12, it's degree 3. And now there's 3 roots, and then the other 3. And you have to be a little careful because there's like an overall scaling factor. You pin it down, but that's enough to determine
Yeah, because like, for example, like this,
So
like,
we don't do a category.
you know, this x1 plus y plus q xy.
Yeah.
And this, like, it's very easy to see they all can do the same graphing surface. By compute this organization, but like, I think that if you do this, like x4, if you do this as like a potential bundle p1 times some p1, and then you can clarify that this is m2. And if you have degree 3 or 4, then I think you got 4.
Spherical functions.
Yeah.
Yes, these are spherical.
Maybe I'll degree 3.
Yeah, Phi is spherical. Yeah, okay,
Yeah, so, yeah, this is not one transform.
Yeah, I won't use
And,
Phi as
but this one,
spherical
if I
functions.
put this inside here, this is, I think this is also right on the surface with 3 single fiber and 1 thing.
Like if you think about like a Fukai kind of thing. Yeah.
And so
yeah, you
this
should
is,
put this as
this,
being-
if I write this one, it's
like
not that
functions
easy
by
to
this,
see.
And then along each of these
But
lines.
what should the
you
fiber
can
text
cycle
be?
there.
Are they
And
still
then
the same?
I think it's all for one.
You get a spherical
One
object inside of the Fukai category of
And-
fiber.
And those
It's
supposed to be
spent
coming
through
from what?
a
That's
spherical
degree 2,
functor
so it comes from
category
plus
of
per
spherical
1.
complexes.
From, you put this like y square as like a, inside this.
Yeah, exactly.
Bundle P1.
Oh.
Yeah. Yeah, if you do this, like, there's a, like, there's something
yeah.
like this, and you choose
Yeah,
a
exactly.
differential.
Okay, category of fiber.
So this is the coefficient of the function. And
Oh, yeah,
then this
probably
equation
should
just,
just be translations, given the audience.
just end up to like this, and then you get a, yeah, you can modify this is right.
But yeah, I mean,
Then
the
this,
idea is behind all
you can
this
have a
is-
lot of choice.
You know, in this case, you should think about like
Uh,
some sources
parameters.
vibrations.
Right,
Like,
so
other
there-
than this,
there-
it's not
so-
that.
so-
Yeah,
there-
I believe this.
No, let me explain. For rational object surfaces, up to transfer star,
Yeah, exactly, so
There
there
are
are wrappings and both.
12
Yeah.
possible configurations of singular fibers that have a non-fixed cross ratio. Okay. 5 of them arise from double star and something which actually is 3
So,
singular
I mean,
fibers.
the way I think about this is like, this is somehow, so you take
It's
this,
not even
a couple of stops.
a
You
variation.
should, I mean, try to do this guy category, so if you do that, you'll get the category.
In transfer, so morally, one of them, so
A2, oh, sorry.
7 of them
It should be
correspond
saying
to
A2,
3 singular
or saying
fibers,
A3,
is 4 singular fiber, I not star. It doesn't even change the J and the so forget those, those are just,
Yeah.
Yeah,
they're
so.
probably safe for
In
certain
a sense, what you
systems.
should be doing here is.
And that leaves
I
exactly
don't, this isn't
5
precise in any sense, but like you should
that
be
have
able
an
to
honest
glue,
modulus.
these two discs together.
All of them have much more complicated fibers than that type.
Actually, that category.
So, you know, if you make the assumption of semi-simplicity, that they're a semi-simple rational object surface, then 4 singular fibers
I
forces
don't know if that's
rigidity.
something people know how to do, but
Four singular fibers.
Rigidity, 4 semi-simple.
Yeah, so you should have like. a
Yeah, because
function you're going
like
to-
for this particular one,
This case,
there's
just
not,
perfect functions.
because like this one, the coefficients here,
Like,
like
the point
this.
is like if you take this category of these stops.
And so,
For that
but,
model.
yeah, although they don't consider this like.
No, but
kind of
the
right,
question is, are these I1?
These are I1.
What's this? Is it IN?
huge.
I don't
Yeah,
know.
just
Okay.
monodrome is like.
Then you're stuck.
So the question is, what are the?
Yeah, because like, usually in physics, they only consider the non-compatible one.
Yeah, but I'm just saying,
Yeah.
if that's the case, then you're
Yeah,
pinned
I don't know.
then that's
Yeah,
absolutely.
yeah,
a
yeah.
situation.
Yeah, I was just, but I'm just
Probably
like,
knows
yeah,
better than I
I was
do.
just trying to
Yeah,
do some
like-
more
like-
calculation on how do I see this
Yeah.
commercialization myself. Because this one I can really
Yeah.
do
so-
it by
okay,
hand,
so-
I can
So
see
assume
that.
instead of this, like I have like
That's the
just a
same
trivial,
thing.
like a product over a disk,
So,
and I put stops on fibers,
yeah, no, let's talk about it next week.
then
Yeah.
Tomorrow's a
if
little
you
easy,
wanna
but
describe the ground chains, these should
we'll
essentially
talk
be
next
like
week.
things
It
that
would be
live
very
above
good
stuff
to
like
get a
that.
copy of.
Uh-huh.
I don't know if that's like strictly true, but.
Uh-huh.
Okay, because I need to see more about the geometry of the configuration of fibers to understand what it's really saying.
So we don't really, okay, so the reason why we see I1 is we know that there's SYZ vibration. The only reason why I know I1 is because on P2, there's like very strong constraints from once I said there exists SYZ vibration on P2 and
P2 minus E.
minus E, I know there's a monodromy at infinity.
Right.
And that will pinch down. The only possibility is just 3I1. Because like, you have three things like multiplied
Okay,
together.
good.
But how do you even know there's, I understand it's a topological argument.
Yeah.
How do you even know there's three?
Yeah, this is like some
Guys, I think we should probably continue.
Alright.
How do you know,
Because all
Yeah.
heuristic.
Yeah, exactly.
Andrew?
Yeah, I think it's.
so there's no
Yeah,
symplectic
exactly, so
singular
you should
fiber
just
that
take
can be
the
equivalence of
intersecting with the fiber
confluence?
here and intersecting with the fiber here, and so on.
Sorry.
So,
That should be the idea between.
we'll talk about it, but I mean, it's
So these are.
not quite obvious.
Oh, okay.
I wanna see the argument.
The functors from like the, I guess what would be like that functor up to category here, just to the fiber. Yeah. Okay.
So Andrew, before you get started, can I ask a silly question? Okay, so you gave a nice example of at least a non-compact surface. I guess I should think of that as function with the cylinder,
With boundary.
with boundaries, there we go. Okay, so a surface with boundaries, that's right, because those are the ends that have the one valence. With sigma empty, does it make sense to consider surfaces without boundary with sigma empty in this theory?
So, I mean, in that case, okay, so one thing that I probably should be saying is that I mean, it doesn't really matter, I can just get rid of these legs, right? Okay, and that's fine, I mean, that's essentially the same thing. But the problem is that right now what I'm gonna do is I'm gonna talk about sort of global sections of these things. So the global sections will depend on the skeleton that you take. So if I take global sections, so in this example, I'll explain this in a second. If I take C to be like dB O or something, and if I take phi to be tensor with the line bundle, then I take global sections of this with this skeleton. So I'll take global sections along a skeleton. What I'll get is like dB co, the projective bundle associated to L, so O plus L, and take dB co of that. But if I take the legs away, if I take one leg away, say, and I take global sections of that reverse sheaf of categories, what I'll get is like dB co of, not dB co, compound. Anyway, some category associated to the bundle L. If I take away the other leg, I'll get some category associated to the bundle, the inverse of L. And if I take away both legs, I'll get some category associated to a C star bundle coming from L. So you take away the zero section of the bundle L, and you get a category associated to that. So this is sort of like, I mean, yeah, the category of global sections depends on which skeleton you take. But so the giving and taking away is just sort of localization. Does this answer the question?
Almost.
Okay.
Helps a lot.
Okay. Okay, so now I want to talk about global sections of these things. And so DG categories within a homotopy category or so there's a model category structure on the category of DG categories called there's two sort of well-known ones. There's one called the Dwyer-Can model structure, and then there's something called the Morita model structure. I'm going to work with Dwyer-Can. But the point of sort of a model structure is that you can
Sorry, which one is structure?
I mean, this allows you to sort of do sort of, treat categories and sort of, well, I'll explain a little bit of how I use this. So, let's see, so we want to take global sections. Of K-coordinatized perverse sheaves of categories. And so, I mean, the most general definition of this is as follows. So definition of global sections is as follows. So if I have a K-coordinatized perverse sheaf of categories, I get a bunch of categories CV, and I can take a product of these things. So B and vertices K. And then to this, get a whole bunch of functors F, B, going to E, so the functors from vertices to edges. And I get that this goes to the product of categories C, E, and and so global sections is the homotopy limit of this. Oh, sorry, homotopy equalizer. It's the homotopy equalizer of this diagram, which is great. It's a good sort of general definition, but it's I'm not going to use this definition to actually do computations with. Okay, but so just to give an example. So if I have K-coordinatized perverse Hilbert, then that, essentially this is the same thing as taking the homotopy limit over the following diagram of categories. So I have A1 goes to twisted complexes over C. I have A2 going again to, and this is the functor F1, A2, complexes over C, and I get to N, to twisted complexes over C. And I'll look at these things, and then I'll look down the purpose of more space. And I have a bunch of these functors coming from the category A, let's see, AN, C, going to twisted complexes over C. This is F1, this is F2, this is Fn, and this is just Fn1. So it's the homotopy limit of this entire diagram of categories.
Andrew, can I ask a silly question?
Yeah.
So the indices on the AIs along the outside there, they're just an index, right? A1 and A2, just it's a label, it's a name for the category, right?
Yes, but you need to keep track of ordering. Is that what you're asking?
No, the AN of C,
Uh-huh.
that AN, is that related to the AN on the right, or is it?
Oh, I
No.
see, sorry, yeah, yeah, this is just unfortunate notation, yeah.
Okay, good.
It's a different AN.
Okay, good. Good. So the AN of C is what I think it is, which is actually related to an AN diagram.
Mm-hmm.
Right, that's where you can find
Yeah.
that. Okay.
Yeah, okay, that's true. Okay, great, so that's, I mean, in this case, what you do is you just take the
But the N
homotopy.
is the same.
Huh?
The N is the same.
The N is the same, yes.
Okay.
I should have maybe used P or something. And so, I mean, in particular, what this is a, so this is equivalent to a, so homotopy fiber product following a diagram. It's called, so you take and C, and you take sort of this map, which is just the map F1, Fn, going to twisted complexes over C, to N copies of twisted complexes over C, and then here is the product of all the categories AI. So it's a homotopy fiber product. So what I'm trying to get at is that, I mean, despite the fact that I'm using sort of this very, I mean, this is not too bad actually, to be honest, but these things can be sort of hard to understand. I mean, when it comes down to it, all you really need is a homotopy fiber product, or sometimes a homotopy equalizer to do these computations.
Why can you ignore other things that doesn't except for this fixed n?
Sorry?
I mean, how can you ignore everything except this fixed n, right? Here you had, I mean, if the k coordinate for Verstrober had, you're saying A2, like A2 meeting an A3, all of these, you're saying you can ignore them?
Oh, no, this is the notational problem here.
Oh,
That AN of C is associated to a Dinkin diagram AN. The only relationship it has to the A's that came before is the index N is the number of A's that came before.
yeah, that's true.
It's not related to the category AN.
Oh, so, sorry, yeah, no, triple notation. Maybe I should call these like BIs or something like that. Is this okay? Does that answer the question? Yeah. Okay. Okay, so it's a homotopy fiber product of this, so maybe just for mostly the sake of culture, I'll explain, I mean, and also for the sake of explaining why the word homotopy is helpful here, I'll explain what a homotopy fiber product is in a very direct way. So the point is that, I mean, I'm taking a homotopy fiber product because if I take a fiber product, I don't get enough objects in this category. I sort of lose a lot of information. At some point I'll also turn around and say that this actually doesn't matter because we chose this category A and C very nicely, but I'll just sort of write this down for the sake of culture, I guess. So here's an explicit model. Nice in the DK model structure. Okay. So let's take F going from a category B1, let's say F1 from B1 to C, 2, so the homotopy fiber product is denoted, so B1 usually it's denoted like this. H to denote homotopy and C to denote the thing that sits in there. And the objects 1, 2 are triples, and this will look fairly similar to what we wrote down before. So N, where A and B, where A is in the objects of B1, B is in objects of B2, and N is in COM F1 A B is closed. And also N is a quasi-isomorphism. And so this specifically means that when you descend to the homotopy category, this is an isomorphism between the corresponding objects. Okay? So so just to point out why maybe why this is a nice why homotopy is nice. So if I didn't pick the word homotopy here, what I would do is I would delete the word quasi-isomorphism. Okay? But if I delete the word quasi-isomorphism, there's going to be lots of things that sort of like look the same that are quasi-isomorphic, but I can't build an object from. And so maybe if I took a category here that was, if I replaced this with some category V1 prime, and some function here that was like F1, but just had, but only agreed on the level of homotopy, then, I mean, it might be possible that this F1, I mean, you could have a functor that goes in here, but all the objects are just quasi-isomorphic to the images of F1, and hence when you take the homotopy fiber product, you might get no objects actually in this category. It's something like this. So, I mean, it's possible to take, we want to live sort of a little dangerously. We want to like let ourselves choose different sort of models for different categories and different functors. And so it's really, it's really important that we actually allow this freedom, which is why we use the word homotopy, why we use homotopy fiber product instead of just fiber products. There's other issues as well. So one of these issues is that, you even see sorts of things when you take like this cone functor on the level of twisted complexes. I mean, when you take a cone, when you take what's essentially a formal cone of a twisted complex, or a homomorphism between objects in a category going to twisted complexes, this isn't going to go. This is going to go to something that's sort of formally equivalent to what you'd expect to be like a mapping code, but it's not. It's going to be some sort of different object. So you can see that there. And some of the categories that we care about, like, if we care about sort of drive categories of cooking and cheese and things like this, there's going to be many different sort of DG structures that sort of give us the same underlying triangulated derived category. And we want to be able to choose which DG structure we want at a given time. And and in some of these cases, the standard functors that you get from maps between schemes and things like this won't give you even honest functors between derived categories, and you have to play through more games. So there's really the word homotopy is really important here, and it's good that we use it. So these are our objects. So homomorphisms are actually, they're described fairly similarly to when we actually defined these categories of I, categories. Homomorphisms are similar to that, so I won't say much about it. Unless you want to see the definition of homomorphisms in this category. It's direct, and I can explain it later if anyone wants to see it. Okay, great. So in this case, so here's a theorem that's actually really easy to prove. Let's downgrade disk proposition, which is that the global sections, so I'll denote global sections of a perverse Schober. I'll just say global sections. PSC associated to a perverse Schober. So that is, I mean, this homotopy limit here, so is equivalent to, quasi-equivalent to the category pi A, where F is the function of functors F1 and Fn, and A is the function of categories A1 to AN. Again, maybe let's use B. Okay. So it's these guys. It's called B. So this just means, so in other words, this means that the homotopy category of the global sections of a perverse Schober has a semi-orthogonal decomposition. Okay, great. So more than that, I had a separate case where you could come up with a perverse Schober in the last lecture. So if you remember, if you have both a semi-orthogonal decomposition on a category with a some sort of DG enhancement, and you have a spherical functor from this category to another category, so that the spherical co-twist is the set functor. Okay. V1, I'm going to be V1, the n, give so D on a category, let's say T, so DG category, pre-triangulated, blah, blah. And we have, so let's say alpha I, iota j. So this is from bj to t. These are embeddings. And we have f from, say, T to another category C. So D. Okay. Is spherical. And the co-twist C F from T to T. So this is an autoequivalence. If this is equivalent to the Serre functor on T of the sum shift by K, then this is something we did last time. Then the composition of Ij Fij, which I'll call this just Fj, is spherical. And we have that it's a collection of functors then plus skeleton K form a perverse Schober. Okay, so that's just recalling what we did last time. So as far as the perverse Schober, so what is the category of global sections? This show. Okay, so that's the question. So what you would expect is that, I mean, so this comes from a category T, plus some data. I mean, what you would hope for is that you can just reconstruct the category T from this. And of course that's true. So but this needs a little work. I mean, it's not a lot of work, but a little work. So this is maybe something that's more should more be called form. Is that sections, or let's say that if let's say A and F are as here, so they come from a spherical functor on T plus a semi-orthogonal decomposition, as just described. Then category pi F A is quasi-equivalent to T, i.e. PSC comes from the data of a semi-orthogonal decomposition on T plus F T to C with cotwist STK. Then I mean the categories were constructed by the global sections construction. And T is constructed by the global sections construction. Okay. So I mean that's kind of not, I guess, extremely exciting. I mean, this is sort of what you would hope happens, and I'm just telling you that what you hope would happen happens. That you can actually rebuild a category from the structure of, you know, a spherical functor with cotwist seret and a semi-orthogonal decomposition. So, I mean, just to give you some sort of maybe place to touch down geometrically, this means is that so this implies that category, how should I say this? So let's take, so how do we get this geometrically? If say okay, so let's just do this geometrically. So if T is equal to dB, let's just go to a very basic example. I mean, this is general, but I mean, we're already going to an example. So let's go to a basic example. In C, dB E, or E, it's a cubic curve. And T has semi-orthogonal composition given by category generated by O P2, category generated by O1, P2, category generated by O2, P2. Okay, it has semi-orthogonal decomposition, and the functor LF from the P2 O E is spherical with curve twist tensor by omega P2 shifted by one. So this is the Serre functor. P2 shifted by who knows? I don't know the number, I think 2. 1? Negative 1? I don't know. Somebody can tell me. So regardless, this fits into our situation. So what this theorem basically says is that, I mean, if so we can reconstruct the co of P2 from the pullbacks, the drag pullbacks of O, O1, O2, and so the point is that if we just look at the humps between the pullback of O, the pullback of O1, and the pullback of O2 inside of DB and E, that these hums are going to be exactly the same thing as the hums of the corresponding objects before pulling back inside of DB and P2, and then we can just sort of use that to reconstruct the category. In this precise example, this is an observation by Bondel and Polishchuk. So in this example, this was observed by Bondel and Polishchuk. I think this observation was like in the early 90s, like 94 or something. I'm pretty sure this is like Polishchuk's master's thesis or something. Like a graduate, whatever. Yeah, okay, so the point is you can just reconstruct DB code P2 from spherical, from certain objects in DB code where you use an elliptic curve. And so you can also ask, what happens if I sort of deform these bundles? I mean, so these bundles live inside of the power group of E, and if I deform these bundles, what happens to the thing that I reconstruct? And so that's going to be something I'll come back to later, and that was sort of why Bondel and Polishchuk were doing this. They were able to, by just deforming this bundle here essentially, so that it was no longer the square of this bundle. But by deforming that bundle, then playing the same game, they were all able to construct all non-commutative P2s. So that's the link with non-commutative functions. Okay, so I guess the last thing I'll talk about is the example that was here that I erased.
So Andrew, does that portion of their argument piggyback on your theorem with Luba? So can you get lots and lots of non-commutative?
So the problem, which we realized fairly early in this, and that was one of the ideas, is that if you take, okay, so DB code E is nice because the curve group is well, it's dimension 1. Right? It's non-zero dimension. If you go, I mean, if you take, you take P3, right? And then you try to do the same thing. You take an anti-canonical divisor and you take the pullbacks of a generator for an exceptional collection on P3 to this thing, I mean, you can't really deform the bundle. I mean, any sort of deformation you take is going to be isomorphic to the previous one. You can't deform these things to 1/7 degree. It becomes a little bit more difficult. But so what we do in those cases is, and this is something I'll talk about next time, is that you don't deform, you don't take a smooth anticanonical divisor like E. You take a singular anticanonical divisor, and you take something where it's not necessarily true that there is a non-trivial Picard group, but you can take non-commutative deformations of the anticanonical divisor, and that's how you construct a certain class of non-commutative deformations at P3. So that's gravity. Okay. So let's look at another example, one that I wrote down. So let's go back to this thing here. Here. So I already wrote down the perverse categories on here. When I start with some sort of autoequivalence on a category, but let's do the same. Let's ask what happens when the category C that I put as the edge category. Let's assume that this is just so dv extension of dv vector space is over K, and let's assume that the autoequivalence is just the identity. So this is trivial autoequivalence. So then I have basically that all the edge categories are just dv vector K, and this autoequivalence around here, the monodromy string. So this is essentially the same that I want to take global sections of the local system that comes from the trivial trivial bundle, so the coefficients in K, maybe C for greatness, and without monodromy. Okay. So what happens if I take global sections? So what is global sections when I do this? So it's a theorem of, I think, Consavage claimed this. Probably proved it, I don't know. But this was proved by Sibylla, Truman, and Zaslow. Maybe more people. That if the global sections, this is equal to dv co of P1. So if I take global sections of this perverse sheaf of categories, I get dv of P1. Yeah, so what happens? So what happens when C is a dv co of some variety x, or x smooth projective, and this phi, the monodromy, this is equal to tensor for some bundle L for L line bundle. On X. That's sort of the question. So, well, we know a couple of things. So the way you should think about this this theorem here is that sort of, this is some sort of singular version of the Fukada category. You should think about like taking partially wrapped Fukada category, things like this, and then things that go around like that, stuff like this. They always go off to the boundaries, or maybe they stick. This in the center here, but it's possible too. Is that so? If you take these things, you can sort of flow them to the skeleton, and then the singularity structure of the skeleton, the A2 a category that you put there sort of encodes, you know, compositions and things like that. So there's objects in this that represents O of 1 and O in dB code of P1. So we have two sort of, so two obvious objects in this category, which correspond to these lines here. So, I mean, the way to do this in terms of the way I've expressed this is maybe not obvious, but you can do it. You can express this in terms of my description of this category. You have something going around like this. So two sort of objects. And if you look at the objects that correspond to the colored lines that I've drawn here, these correspond to O of P1, O of 1 of P1, and the orange one corresponds to O of P1. Anyway. Okay, so these two objects give you an exceptional collection in the category, the category of global sections, and then what you see is that these objects generate the category. So the way to think about this is that, I mean, what is this category? So this category is going to be a homotopy fiber product of A2 of K and A2 of K. So objects in A2 of K are triples, and so if you take the object just K, 0, 0, so the first object is K, the second object is 0, and the homomorphism between them is 0. And you take the same thing here, K, 0, 0. These things will, these will give you an object in the homotopy fiber product, along with just an identification between K and K, so some sort of identity map. And then similarly for the purple thing, I mean, so you see that this is like, you know, the cone of this thing is just K, and the first thing is just K, and the last thing here is 0, so that's why I've drawn nothing here, but orange here and orange here. Okay, so this, you have sort of a diagrammatic way of describing objects in this category of global sections. Right, so this gives you a semi-orthogonal decomposition, and on the other hand, so the category, so dB code of the projective bundle X associated with O plus L, so has a semi-orthogonal decomposition as well, and it looks like just dB code of X and dB code of X. So what you should try to do is you should take the perverse sheaf of categories coming from this data. So monodromy around here, so the Boolean functor here is going to be tensor with L, the Boolean functor here is going to be trivial, and blah, blah, blah. So what you do is you sort of take objects that live along here that are 0 when you map down here, and 0 when you map up here, and conversely you take the subcategory of objects which are 0 when you map down here, but not 0 when you map up here, and you build a semi-orthogonal decomposition on the category of global sections. And so the theorem is the following. And is that the category of global sections on the equilatized perverse sheaf of categories on S1 plus S1. Let's see, with K, this skeleton, and sigma, the empty set, and monodromy trivial, monodromy tensor L, and general category C given by X. So the category of global sections on this is the project DB co throughout the category of coherent sheaves on the projective bundle X OX plus L. So, you should think about this as maybe some sort of version with coefficients of this theorem of Sibylla, Troyman, and Zaslow. So I explained in some vague sense like how this is proved. You just show that there's a semi-orthogonal decomposition coming from natural subcategories, and then you show that that semi-orthogonal decomposition is actually going to generate your category. You have two semi-orthogonal segments. So this is true. So what does this mean? So how should you maybe interpret this in terms of mirror symmetry? So this suggests the following thing. If V12 of X is equivalent to, say, E pi of some manifold M, so you have mirror symmetry between X and M, and some symplectic automorphism. Let's give it as G from M such that G acts on M sort of D pi. Identically to tensoring with L on X. Okay? So we have two actions. I'm assuming that G gives an action on the Fukati category, which agrees with the action by tensoring with the line bundle on dB of X. Okay. So then let maybe script M be the vibration over some punctured disk, maybe delta star. Let's just say S1 is 0.1 with monodromy given by G, with symplectic monodromy. Okay, so then what this suggests is that the wrapped Fukaya category, so is the wrapped Fukaya, partially wrapped Fukaya category. Let's call this just I'll state this as a question more than actually a conjecture. So this is partially wrapped with sort of stops at the at each of these endpoints is equivalent to dB P X O X. So my question is that true? I mean that seems to be sort of what you might expect from the construction. I mean this should be somehow, I mean, if you have this sort of vibration, you would expect that you get some sort of analogous perverse sheaf of categories on the cylinder, and that the global sections construction will be the same. So this is my suggestion. Let's see. I don't know how much time I have, or how much more material I have for today. Yeah, I was going to go into another example, but that's about it. So maybe that'll be.
In the last thing, the script end is vibration with a generic fiber, your amount, simply the amount for capital N. Is that what you meant by vibration over that cell?
Oh, yeah, so I want every fiber to be symplectomorphic to M omega, and I just
So
want.
that's a general fiber, and what happens to a singular fiber?
I don't want any singular fibers.
Oh, it's a smooth bundle.
Yeah, it's a
Oh, that's a bundle.
Yes, yes, yes.
Oh, so-
Yeah.
Is there any other question for Andrew? I might have also in the end. Do you have a non-visual model on the A side structure? Model case?
On my quick side?
Yeah.
Is there a
You have
line
a
of
super
example?
potential.
I mean, yeah, essentially what you should be thinking about, another way to think about this is that like, I have a Landau-Ginsburg model over some open piece of C star, or some sort of mapped open piece of C star that I compose with the Landau-Ginsburg mirror, Landau-Ginsburg potential x plus 1 of x of P1. And then like, so, yeah, I mean, so what I'm giving you is some sort of map to C star with monodromy that I compose with this. And then what I'll have here is like a Landau-Ginsburg model over the disk. And yeah, so it should be, yeah. I think there should be a Landau-Ginsburg model. I mean, what you should be doing then is just taking the partial wrapping with respect to the composition of these two functions. But I don't know like how to do this computation at all.
If not, let's do it again. Really?
Oh, yeah.
I have no idea.
Oh, okay.